Hello. I'm currently in Indonesia when I record this video, and actually in my hometown. So there's a chance that my signal is not that strong and the recording is not that perfect. But I hope by seeing the notes later on, you may see you can get a clearer view in case the recording is not clear. Okay, let's start. Today I will cover 15.6 and 15.7. The material today tends to be quite short when it comes to the explanation, but you will see the devil is actually in the details. So you will see the explanation will be short, but I will try to spend more time on the exercise. But you will definitely need to practice more, okay, and try to take advantage of my supplemental video on these sections. Okay, let's start. In this 15.6, we'll be covering surface area. Section 15.6, and use that surface area. Okay, here's the idea. Suppose we have a surface on, let's say this is the surface here. Okay, now, and we want to find the surface area of this F here. Let's call this S. Now you will see the domain of this surface on XY plane will be called D. Now we have seen before when we did the tangent plane thingy. Suppose I take a tile. Suppose I take a tile on the surface here. May not be horizontal. May not be horizontal. Well, let's say something looks like this. Okay. Now, if I take this tile, now I hope you remember that at that time we represent this factor here as factor, let's call that factor A, which is which is 1 unit in X direction, 0 units in the Y direction, and F sub X unit in the Z direction. Now, likewise, for the one here, let's call this factor B. We can represent this by factor 0, 1, F sub Y. Okay. Now, then the area of this tile here, let's call this DS. The area of this tile here is equal to the magnitude of the cross product of A and B, dA. Basically dx times dy. Okay, now which if we compute A cross B, again, we did it before. When we compute A cross B, I, J, K, 1, 0, Fx, and then 0, 1, F sub Y. This will then be negative Fx, negative Fy, and then 1, such that the magnitude of A cross B will be the square root of f sub x squared plus f sub y squared plus 1 squared, which is just 1. Okay, so going back to that differential of the surface area, this is actually the square root of f sub x squared plus f sub y squared plus 1 dA. Now, you may wonder what is dA. We basically get you see this tile here, if I move it further. So let's say this tile here, this is the ds, right? Now, if we do the shadowing to the domain, this is the dA. In other words, what we get actually, the ratio of the area of this tile here to the tile on xy plane, so which is the shadow of that blue tile. Okay, so we are basically saying that the differential area of that blue tile is this coefficient multiplied by the area of that yellow tile. Okay, now with that said, then the total surface area, so surface area S is equal to, maybe I write it this way, area of surface S is equal to double integral. Usually we denote it this way, by the way, double integral of S ds. Now, of course, that kind of notation doesn't help at all, right? And then we convert this double integral, instead of with the domain S, now we make it in domain D. But once we project that down to xy plane, then I need to rewrite the ds as that square root of f sub x squared plus f sub y squared plus 1 dA. And that's the formula. Okay, that's the formula. Now you will see that to compute the surface area, that's basically the extension of finding the tangent plane. But when we did tangent plane, all we did was actually using this factor, right? This factor is normal to the ds. Okay, this factor is actually, if I go forward, this factor is actually normal to this tile, blue tile here. Just the cross product, right? Okay, now the length of that cross product is equal to the area of that blue tile. Okay, and that's it for this. Now, what we need to do next, of course, is to do exercise. Okay, like what I said before, I will do some exercises here, but that will never be enough. You need to do your own exercise. Okay, and of course, try to benefit from my supplemental videos, especially the one on this section. Okay, example 1. You will see I pick example 1 and example 2 actually from the book. So the first one, find surface area. Find surface area of a surface given by z equals to x squared plus 2y over the domain D, over domain D, which is a triangular region on XY plane with vertices uh, 0, 0, 1, 0, and then 1, 1. So there are two things we need to work on here. First, let's figure out the domain first, okay? So the domain will be a triangular region with vertices 0, 0, 1, 0, and 1, 1. So that's the domain. Okay, now then the boundary, this is y equals to 0, this is x equals to 1, and this is y equals to x. Okay, now why we need to find that domain D on the xy plane? Because that will help us later on to set up the integral. Okay, the integral later on will be a double integral. X is from 0 to 1, right? And then the y will be from 0 to x. Okay, we save it for now like this. Basically, we want to see the domain of integration, the domain of that surface to help us to have the domain of integration. Now, secondly, the integrand. What happened with the integrand? Well, we have z equals to x squared plus 2y. So c sub x is 2x, and c sub y is 2. Now, what happened then with the square root of z sub x squared plus z sub y squared plus 1? That will be square root of 4x squared plus 2 squared plus 1, right? Okay, well, we can write that as square root of 4x squared plus 5. Now, putting these two together, the domain of integration and the integrand of integration, then we get the surface area. Okay, so the surface area, like again, let me write it at the area of surface S will be equal to integral from 0 to 1, integral from 0 to x of square root of 4x squared plus 5 dy dx. Okay, I do assume at this point that you are pretty good with your integration though. Okay, so the focus will be on the setting up. Okay, when for us to set up the double integrals for this surface area, you need two things. First, you need to know the domain of integration. Second, you need to know the integrand. Okay, then I would integrate all because the inner integral, inner integral is with respect to y, but the integrand has no y's. That's basically the length of the interval. I was talking about this. If you integrate this, if you integrate that, then you will see that's basically the length of that interval. The integrand multiplied by the length of the interval, because the integrand is a function of x only while you are integrating with respect to y. Okay, now then from here, when we integrate, I need to do u substitution. Let me scroll down. So du equals to 8x dx. Okay, and then u sub 0 is 5. U at 1 is 9. Okay, and then just integrate it from there. We get this is 5, this is 9, then u to the power of 1/2 and du over 8. Right? That will give us 1/8 times 2 over 3 u to the power of 3/2 from 5 to 9. What is that? 1 over 4. Okay, and then 9 times 3 minus 5 square root of 5. That is 1 over 12. 27 minus 5 square root of 5. I hope I don't make miscomputation though. Why I feel like the numbers so strange. It seems to be okay. It seems to be okay. Yeah, well, you can check with the book, right? Yeah, you can check with the book if that is the solutions. I took it from example 1. Yeah, I took it from example 1. Okay. Let's go on with example 2. Give me a second. Why? I have my notes on that, but I didn't work it out fully. But let me check with the book if that's the answer. I feel like I make some mistake. Oh yeah, I did it right. Oh, surprise. Okay, let me go on with the second example. Again, this example is from our book. And the question is example 2. The question is find the surface area of surface S given by C equals to x squared plus y squared under C equals to 9. And I hope you remember C equals to x squared plus y squared. That's basically C equals to r squared, right? When we try to graph that in 2 dimensions, it looks like if this is r, this is C, that will be a parabola, right? But then because this is 3 dimensions, we will rotate that, revolve that with respect to the z-axis. Okay, now we have a paraboloid, right? Then the thing is supposed to, you have a surface or a plane capping that paraboloid. The plane is C equals to 9. Then what is the surface area for on that paraboloid? Below that plane. Okay, including the one at the back. Then you will see if we take the shadow of this surface here, you will see that we basically set it this way. X squared plus y squared has to be less than equals to 9. We have r squared less than equals to 9, so r is less than equal to 3. So the domain is actually on 2 dimension xy plane. The domain is actually a disk with radius 3. Okay, that's a disk with radius 3. Now, so our integral later on seems like we will move in the direction of polar integration, but let's worry about that later on. Let's see the integrand first. The integrand c sub x will be 2x, z sub y will be 2y. So the square root of c sub x squared plus c sub y squared plus 1 will be the square root of 4x squared plus 4y squared plus 1. Okay, so the surface area is equal to double integral over d, if this is d, okay, of square root of 4x squared plus 4y squared plus 1 dA. Okay, but the shape of the domain seems like it is easier to deal with in polar, and at the same time, the integrand will give us a simple functions when we write that in polar also. So you will see when we set up the d in polar, that will be radius from 0 to 3. Okay, actually no, the theta is from 0 to 2 pi, and then the radius from 0 to 3, square root of 4r squared plus 1 r dr d theta. Okay, notice that it is independent of, the integrand is independent of theta, and the domain of integration is quote-unquote a rectangle. The domain of integration is quote-unquote a rectangle. In other words, they are all numbers. Okay, the domain of integration, the limits of integration for r is independent from the limit of integration for theta. Okay, so then you will see we can actually do it this way. This is integral from 0 to 2 theta, 2 pi of d theta multiplied by integral from 0 to 3 of square root of integral from 0 to 3 square root of 4r squared plus 1 r dr. Okay, now integral from 0 to 2 pi of d theta, that's just the length of interval 2 pi. But if I do substitution here, u equals to 4r squared plus 1, then my du will be 8r dr. And u at 0 equals to 1, u at 3 equals to 37. Okay, so my integrals now from 1 to 37, u to the power of 1/2 du over 8. Okay, that's pi over 4 times 2 over 3 times u to the power of 3/2 from 1 to 37. And then simplify further, computing plug-in numbers. This will be pi over 6. Okay, 37 square root of 37 minus 1. Now, u to the power of 3/2 is the same to u times u to the power of 1/2, right? U square root of u. Okay? Let's do some problem from our textbook. I start with the easiest one first. Question number 2. Let me screenshot that. Question number 2. Let me put it here. Find part of the plane to x plus 5, y plus b equals to 10 that lies inside the cylinder. Think of it this way. So you have a cylinder. Okay, that you cut with a plane. So let's say this is your plane. This is the plane. This is the cylinder. Now you see that the S that we are talking about, the surface, the area of the surface that we are looking for is the area of that blue one. However, the domain, which is a disk with radius 3, is underneath here. Okay, so this is our S, and this is our D. Okay, now then, how about the integrand? Well, we need to rewrite that first. The plane is given by z equals to 10 minus 2x minus 5y. Therefore, c sub x is -2, c sub y is -5, such that the square root of c sub x squared, I'm sorry, Indonesia is quite humid, and I tend to have my allergy coming back to Indonesia. Yeah, every time I come back to Indonesia, I need to overcome this allergy. This is square root of 4 plus 25 plus 1, that's square root of 30. Okay, so notice that then our integrand, the surface area of surface S, has double integral over d square root of 30 dA. Is it right? But this is equals to square root of 30 double integral over d of dA. Now, again, if you think about it, this integral here, this is area of d. Okay, that's area of d. In other words, this is equals to square root of the area of S is square root of 30 multiplied by the area of D, which is 9 pi. Okay, the radius is 3, right? Okay, so the area of surface S is 9 square root of 30 pi. Now you will see we will have this phenomena in which the integrand becomes a constant if the surface is a plane. Okay, the integrand is a constant if the surface is a plane and the area of that surface S is basically the square root of 30 or square root of whatever, that's the thing there, multiplied by the area of the shadow in the domain. Okay, that's for number 2. The next one I would like to work on. Now, the questions that I work on here happens to be, some of them happens to be a case that worth mentioning. So let's see, question number 8. I think nothing really special about this question number 8, but I want to emphasize that don't rush to your integral too early. Okay, don't rush to don't rush to this too early. Don't rush to these too early. This thing, don't rush to these too early. No, focus on the setup of the domain and setup for the integral. Okay, if you did either one of these wrong, then whatever integral you get is already wrong. Okay, so be patient with setting up the integral. If you set it up properly, then the integral tends to be something flowing quite easily. It's not always the case, but imagine if your setup is already wrong, then whatever you do after that will be just waste of time, right? Okay, so let's see this one here. Solution. We have that c sub x, therefore just x to the power of 1/2, and c sub y will be y to the power of 1/2, right? Okay, such that the integrand square root of c sub x squared plus c sub y squared plus 1 equals to square root of x plus y plus 1. Now, the domain of integration happens to be a nice one. It's a square from 0 to 1 to 0 to 1. Okay, now, let's see. The devil may be in the details. So the surface area, the area of S, is given by integral from 0 to 1, integral from 0 to 1 of square root of x plus y plus 1 dy dx. Unfortunately, the integrand is not separable. So we need to do substitution, and that substitution may not be an easy one. Okay, so u equals to x plus y plus 1, and we will do the differential with respect to y. Okay, why times do we do that with respect to y? Well, because our first integral, we need this thing. That's what we need, right? We need this thing. Okay. But what happened then with the limits of integration? Well, when y equals to 0, then u0 will be x plus 1. When y equals to 1, then it becomes x plus 2. Okay? In other words, our integral now, due to that substitution, we'll have integral 0 to 1, integral of x plus 1 to x plus 2, and then u to the power of 1/2 du dx. Okay, and then we will have integral from 0 to 1 of 2 over 3 u to the power of 3/2 from x plus 1 to x plus 2 dx. Okay, x plus 2 to the power of 3/2 minus x plus 1 to the power of 3/2. Sorry, this is supposed to be an integral. From 0 to 1. Okay, and then from there we integrate further. I get 2 over 3, and then 2 over 5, x plus 2 to the power of 5/2 minus 2 over 5, x plus 1 to the 5/2 from 0 to 1. Okay, notice I can factor the 2/5 out, so I get 4 over 15 outside, right? But then inside, I will get 2 to the power of 5/2 minus 1 to the power of 5/2. And then, is it right? No, 3, huh? When I plug in x equals to 1, it should be 3 to the power of 5/2 minus 2 to the power of 5/2 minus, when x equals to 0, then I get 2 to the power of 5/2 minus 1 to the power of 5/2, which is just 1. So what will this be? This is 4 over 15, 3 to the power of 5/2 minus 2 times 2 to the power of 5/2 plus 1. 3 to the power of 5/2 is 3 squared, square root of 3, minus, that will be 2, 8. 8 square root of 2 plus 1. Okay, that's for number 8. Let's see more. I think I have one nice question here. Number 12. Let me screenshot for you. Part of the sphere that lies inside the paraboloid. So let's say we have a sphere. Okay, let me draw it in 2 dimensions first. We have this sphere, okay, given by r squared plus c squared equals to 4c. Okay, And then that lies inside, let's actually rewrite this first. This is r squared plus c squared minus 4c equals to 0. When I complete the square, I add 4 both sides. So c minus 2 squared equals to, oh, it looks like this actually. So it looks like this. The center is 0,2. Okay, that lies inside the paraboloid c equals to r squared. So c equals to r squared, it's a parabola, right? But what we want is actually just part of the sphere. Just this part of the sphere here, this cap here. Now I need to see that in 3 dimensions. Okay, so we are actually dealing with the area of this blue cap here. Okay, we look, find the area of that blue cap. Now then let's find the intersection first, and from there we can bring the radius, and therefore we can find the domain of the integration, right? We expect that to be this though. Okay, the domain of that. Let's see. So we have z equals to x squared plus y squared. Okay, and we have x squared plus y squared plus c squared equals to 4c. Okay. Okay, so when I do the substitution, then I get z equal plus c squared equals to 4c. So c squared equals to 3c. So we get, what's that? Z equals to 0 or c equals to 3. And it makes sense, right? You see that the paraboloid and the sphere actually intersect at 2 different places. The first one at the origin and the other one at the boundary of the caps, right? Okay, but what are the r at that time? Well, we plug that back here, right? When we plug that back there, then we will see that x squared plus y squared equals to 3. Oh, so it's actually a disk with, the boundary is actually a circle with radius square root of 3. Okay, with radius square root of 3. Okay, now next I need to find the integrand. Okay, I need to find the integrand. We already have, we have that x squared plus y squared plus c squared minus 4c equals to 0. When I complete the square, x squared plus y squared plus c minus 2 squared equals to 4. Okay. What I'm about to show you is just a regular way, a standard way. No, I should not say standard. The way we usually do it in the past to find the c sub x and c sub y. Basically, I will solve for z first. Okay, and then I do the square root. Notice that we will take the top part of the sphere, right? Therefore, when we do the square root, we only take the top branch. It's supposed to be plus minus square root, right? But I will take the top branch only, okay? Supposed to be plus minus, right? But because we take the top part of that sphere, we take only the top branch, and z, therefore, equals to 2 plus square root of 4 minus x squared minus y squared. Now the c sub x, therefore, becomes negative x over square root of 4 minus x squared minus y squared. Now you will see it's actually something over 2 square root of 4 minus blah, 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 but on the top you get negative 2x and the 2 cancels. Okay, now likewise, if we do the c sub y, we will get negative y over square root of 4 minus x squared minus y squared. Now then when we get the square root of c sub x squared plus c sub y squared plus 1, we get x squared plus y squared over 4 minus x squared minus y squared plus 1. Okay? And if you combine like, do the LCD, combine like terms, then you will get, on the top, you will get square root of 4 right at the top. You try. And at the denominator, you will get 4 minus x squared minus y squared. Okay, now let me leave it here for now. I said earlier that this is the usual way we do it, right? To find this guy, we basically solve for z first, and then do the c sub x, c sub y, so on and so forth. Now, what I want to say is, actually, no, we don't have to do it this way. We can just do implicit differentiation from here. Okay, we can do implicit differentiation. When we do the implicit differentiation, then I will get I will get 2x plus 2z c sub x equals to 4c sub x. Implicit differentiation with respect to x. Okay, so c sub x of 2z minus 4 equals to negative 2x. I can factor 2 and cancels, right? So then c sub x equals to negative x over negative x over c minus 2. Okay, now let me ask you to compare that. C sub x equals to negative x. So we match this part, but the denominator c minus 2 is this part, right? Okay, do you see that? Okay, so you can do the implicit differentiation. You get the c sub x first, right? And then similarly, c sub y will be negative y over c minus 2. And then when you put them together, c sub x squared plus c sub y squared plus 1, that is equals to x squared plus y squared over c minus 2 squared plus 1, right? But your c minus 2 squared equals to what? When you add 1 equals to what? You may consider this way of doing it, but in the end, you will see when I combine like terms and change that c minus 2 squared in terms of xy, I will get 4 over 4 minus x squared minus y squared. Okay, so when I put under square root, this is what I get. Okay, the same way. Now let's go to the setup, the integral. Okay, so the surface area of S will be double integral over domain D of 2 over square root of 4 minus x squared minus y squared dA. And you see that the domain looks like this with radius square root of 3. Okay, so it is easier to deal with that in polar, right? So integral from 0 to 2 pi, integral from 0 to square root of 3, 2 over square root of 4 minus r squared r dr d theta. Okay, so we get 2 pi. Okay, substitution 4 minus r squared SRU. So du will be negative 2r dr. 2 pi And as for the domain of limits of integration, u0 will be 4 and u square root of 3 will be 1. Okay, so integral from 4 to 1 of negative du over u to the power of 1/2. Okay. See, 2r dr is equals to negative du. But that's 2r dr is negative du. So you see that I substitute that with this. Okay. Anyway, then when I integrate that, I get that 2 pi. You know what? Let's do this first. Integral from 1 to 4 to absorb the negative and u to the power of negative 1/2 du. Okay, and that will give us what? 2 times u to the power of 1/2, right? From 1 to 4. Which is 4 pi 2 minus 1, which is just 4 pi. Oh, I don't expect that to be such a nice number. Okay, that's for number 12. I think I'm actually done with this part here. I want to do one more question. I happen to see this question and consider this something special. From our textbook, that will be question number 23. I don't know if that's something special, but I think it's more about that, hey, you know what? This question seems to be interesting. What is that? What part of this that is interesting? The way we need to massage the question. Okay, what part? Notice that we are required to find the area of the finite part of the paraboloid, but notice that this paraboloid is not opening up, but opening to the right-hand side. Okay, so the paraboloid is actually y like this, right? So the paraboloid is actually like this. Okay, cut off by the plane y equals to 25. So cut off by plane, that's a vertical plane, y equals to 25. Okay. The domain of integration, of course, if you project that to the XC plane, you will see that's actually a disk with a radius 5. Okay, let's see. So when I set y equals to 25, but at the same time that y is x squared plus c squared, right? And you see that's actually x squared plus c squared equals to 25. That's the boundary of the domain, which is actually a circle with radius 5, right? But the area that we are looking for, the area that we want to compute is the area of this paraboloid. Okay, that's the area of the paraboloid that we are looking for. Now, usually we have x squared plus y squared equals to c, but in this case, it seems like the role of x and z being switched. Now, then that's actually what makes this question something I want to go over. Okay, so the hint is like, notice x and c, the roles of y and c are switched. from the way we usually treat them. So basically then we will treat our y now, our c now as if it were y in the past, and our y as if that's a c in the past. Okay. What I want to say is this, then we are not looking for c sub x, we will look for y sub x and y sub z now. Okay, notice because the surface is defined with y equals to a function of x and z, right? Okay, so this will be 2x, this will be 2z, therefore y sub x squared plus y sub z squared plus 1 will be 4x squared plus 4c squared plus 1. Put them under square root. Okay. Now we will make it polar later on, but our polarization, the way we polarize that, instead of like x equals to r cosine theta and y equals to r sine theta, we will make it c equals to r sine theta. Okay, so our area of surface S now is double integral over domain D, this one, this D here, of square root of 4x squared plus 4c squared plus 1 dA. Okay, but then when we make it polar, that's from 0 to 2 pi, the radius is from 0 to 5. Okay, square root of 4r squared plus 1 r dr d theta. Okay, and I believe you can just compute it from there. Okay, we did this many times though. This is for 15.6. This is for 15.6, and suggested homework for you from this section will be number 1 to number 12. Number 24, I think, is actually another interesting one. 21 and 24. Yeah, 21. So 1 to 12, 21 to 24. Oh, I forgot to write it down. So suggested homework from section 15.6, that from number 1 to 12, number 21, and then number 24. Again, number 24 is actually an interesting question. It depends heavily on your ability to visualize the three-dimensional situation. Okay, now let's go on to the next section. Section 15.7, triple integrals. Now, oh, this section here is heavy, very heavy, very heavy. Why is it hard? You will see that we will need to be able to set up the integral. The challenge will be in setting up the integrals based on the solid we see, the solid in 3 dimensions. Now, let's get the idea first. Okay, the idea. I believe I already give you this little idea originally earlier. We have seen how we develop double integral over general domain. So if we have the general domain D like this, and the solid is bounded above by the S, right? Now we want to find what is the volume of this solid. And the way we did it, we had the volume is equals to double integral over d, okay? And on the top we have that s, which is given by f of xy dA, okay? This is the solid bounded above by surface S and bounded below by xy plane, right? Okay, now, which using augmentation so this technique of augmentation being used a lot, right? We get, again, augmentation is basically a technique where we solve that problem by looking at one dimensional higher. Okay, so this volume now can be rewritten using triple integral instead, double integral over d, and then that fxy now we represent as integral from 0 to fxy dz. That will give us simply fxy, okay, and then we continue with the outer integral dA. Okay, so notice that this triple integral give us the volume of the solid bounded above by S. This is so this is the volume, quote unquote, volume of solid E. Let's call this solid E here. Okay, bounded above by S and below by xy plane, which on the first day of our class, you remember xy plane is given by c equals to 0, right? Okay, so on the top, it is bounded by S given by Z equals to fxy and bounded below by C equals to 0. So that's what it looks like. This is the upper bound, this is the lower bound. Upper bound, lower bound. Okay, now, if solid E is instead bounded by Z equals to Gxy, then the volume now becomes double integral over d and then integral g to f of dc dA, right? Okay, so this lower bound, bounded below, I think I need to clarify that. Bounded below by. Then we have that. Let's extend this a bit further. If the density is rho as a function of x, y, z, okay, so the density is not now constant, it varies, depends on the position, then the mass, quote unquote, of E is given by, I use quote unquote here because the density doesn't have to be a positive number, and it doesn't have to be reinterpreted as a mass all the time. Okay, but a mass of solid E, one way to compute that is by doing this triple integral over D, which is the domain on XY plane. Okay, and then GXY, integral of GXY to FXY of rho XYZ DC TA, where the DC is for the innermost integral, and as for the dA, that's the double integral on the outside. Which you will see we may rewrite as triple integral over domain E. So the domain of integration now is not two-dimensional, but three-dimensional E. Okay, rho XYZ dV. Okay, so this guy here may now be written as dV. I'm about to do examples from here. Okay, but before I start working on that example, there's one important note to mention, and this is the I try to point out the difficult part of this section. Okay, now notice the following. Notice what makes this section hard when we start working on the problems later on. By Fubini's theorem, okay, we now have think about this statement a little bit. Okay, we now have 6 orders of integration. In rectangular. The one we used above was dC dy dx order, right? But of course, we may have the dC dx dy. Of course, when we change the order of integrations, we need to change the limit of integration as well. Okay, another order is a dy dC dx, or dy dx dz, or dx dC dy, and dx dy dc. Those are 6 possible order of integration in rectangular, of course, and let me use green color, and more if we consider R dC d R dC dr d theta. R dC dr d theta. Now, of course, dC dr d theta, we may play around with the ordering again. There are 6 more orders there, right? Okay, so in total, actually, we have 12 possible orders of integrations. Okay, now, why I mention this? Because while we have many orders of integrations, not each one of them give us the same ease, or another way to say that, not each of them give us the same difficulty to compute. So one order for integration may be too hard to work on, but then when you see that from another order, it turns out to be easier to do. Okay, so the challenge again is on how to set them up first. Okay, the challenge is on question. Let's take a look on example 1. I will work on problem from the book, example from the book first. Let me screenshot the situation. Give me a second. So this is example 1. Evaluate the triple integrals where B is the rectangular box. So the B there stands for the box, right? The nice thing here is the domain. Because it's a box, then the X is constant to constant, the Y is constant to constant, the C also constant to constant. Okay? So our triple integrals will be integral x, y, z squared, dc, dy, dx, right? Now, with that said, then the dx should be in the outermost. Okay, x will be from 0 to 1. As for the y, that will be from -1 to 2. And the innermost dc will be 0 to 3. Okay, now don't forget, notice that the domain basically quote-unquote rectangle, right? Because it's all constant, and the integrand happens to be separable. Okay, so we can do this triple integrals as the product of 3 simple integrals. You see what I mean? Not always doable though, only if the domain of integration is a box and the integrand is separable. Okay, so this becomes 1/2 x squared from 0 to 1 times 1/2 y squared from -1 to 2, and then 1/3 c cubed from 0 to 2. Okay, this is 1/2 times 1/2 of 4 minus 1 times 1/3, 27 minus 0. Okay, so this is, this cancels. So 27 over 4. You see that the computation is not on the hard side yet, right now. Okay, but the methods of integration that we have in the past, if the domain of integration is a box, is a rectangle, and if the integrand is separable, then we can rewrite that as the product of 3 integrals, 3 simple integrals instead. Okay, now let's go on further. Let's work on example 2 from our textbook. Yeah, after I'm done with this example 2 in our textbook, or maybe another example from our textbook, then I will do problems from our exercise set, some problems from exercise set. But of course, then you need to practice even more, right? Okay, we have these triple integrals right now. Triple integrals over E of z dv, where the solid of the tetrahedron is bounded by x equals 0, y equals to 0, c equals to 0, and x plus y plus c equals to 1. If you remember the technique that I showed you before, how to find this plane, is basically by looking at the x, y, z axis intercepts, right? And we know this is actually 1, 1, 1 in in the first octet. Okay. Solution. I will first show you how to see this in look at the shadow on XY plane. Look at the shadow on XY plane. If you look at the shadow on XY plane, you will see that's actually a triangle, right? This is our D here. Okay. So the outer two integral will be double integral from 0 to 1 for dx, and then from 0 to 1 minus x. See, so notice that on xy plane, the c equals to 0, right? The c is equals to 0, so we get x plus y equals to 1, but when we solve for y, we get 1 minus x. Okay, so from x from 0 to 1, for any x I choose, then the y will be moving from 0, going into the solid from 0, from y equals to 0, and going out from that solid at y minus x. Okay, now how about the innermost integral? If I choose a point here, let me use red color. If I choose a point here, which in our 3-dimension, let's say is that point, then it will start from c equals to 0 and going out at that plane, right? Okay, so the c will be from 0 and going out at that plane, which is 1 minus x minus y. Can you follow me? Okay, now this is the setup. Now I want to say that you will see later on when I do it another way, this setup may not be the easiest to work with. Okay, but let's do that anyway. So when I integrate this integral from 0 to 1, integral from 0 to 1 minus x of 1/2 c squared, this is what I will get. Okay, so when I do the innermost integral, right? And then from here, I need to do substitution. U equals to 1 minus x minus y, du equals to negative dy. So when my y equals to 0, my y equals to 0, I get 1 minus x. When my y equals to 1 minus x, I get 0, right? Okay, so my integral now becomes integral from 0 to 1, integral from 1 minus x to 0 of 1/2 u squared negative du of dx. Integrate again, I will get 1/2 times 1/3 integral from 0 to 1, okay, of u cubed from 0 to 1 minus x. I reverse the order of integration, the order for the limits of integration by solving the negative sign, okay? And that will give us 1/6 integral from 0 to 1 of 1 minus x cubed dx. Okay, and of course you can integrate this, right? Okay, let's v equals to 1 minus x, so dv equals to negative dx. When x equals to 0, the v is 1. When x equals to 1, the v is 0. So this is 1/6 integral from 1 to 0 of v cubed negative dv. It's 1/6 times 1/4. 0 to 1. Oh, that's 1/24. Okay. Now, suppose I show you another method. I don't know if this is easier, but imagine my domain of integration is actually, so the second solution, if my domain of integration is actually xz plane. So if you see that from the right hand side, this is my x, this is my c, I get this. Okay, where this is x plus c equals to 1. Okay, now then my inner integral will be integral from 0 to 1, integral from 0 to 1 minus z, okay, of dc in the outermost, dx in the middle, and my innermost integral will be from 0 to 1 minus x minus c. We have a z here. How do you get that innermost integral, Thomas? Well, okay, so suppose I choose one c, a value of z, then my integral, my solid will come in at x equals to 0, at x equals to 0, and it will come out at x equals to 1 minus z, right? Okay, now then, for any coordinate xz that I choose, when I go, so in this solid up here, if I start from the left wall, choose a point there, okay, and I shoot to the right-hand side, I will start from y equals to 0, but come out at that plane, right? I will come out at that plane. I will come out at this plane here, but the equation of that plane, if this, when I solve in terms of y, that will be 1 minus x minus z. Okay? So that's the setup. Now you, going back, Thomas, you say this method may be easier. The second way of doing this may be easier. Why? Now, I'm not saying that it is always easier using this method though, but notice that the integrand of the integration consists of only z, right? Okay, so you may want to avoid z as much as possible since the beginning. Okay, so when I integrate with respect to, when I integrate with respect to y, notice that that c is actually something I can move a lot forward. I can move it this way: integral from 0 to 1 z, integral from 0 to 1 minus z, integral from 0 to 1 minus x minus z, dy, dx, dz. Think about it. Because I will integrate but with respect to z last, so I can pull that integrand c actually until my last integration. Okay, so in my first integral, in my innermost integral here, notice that that's just length of interval. It's actually 4:34 in the morning right now here. Okay, and this happens to be on the fasting month. And if you hear those sounds, that's my Muslim friends actually praying in the very early in the morning. Okay, you know, they pray for 5 times a day, right? Okay, now anyway, how to integrate this? Oh, I need to do substitution now. So u equals to 1 minus x minus z. I do the differential with respect to x. Okay, and then my limit of integration when x equals to 0, my limits of integration is 1 minus c. If my x is 1 minus c, the limit of integration is 0. Okay, then when I plug that in, I get integral from 0 1 to 1 of c, integral from 1 minus c to 0 of u negative du dz. Okay, I will absorb the negative by reversing the limits, the order of the limits of integration. So I will get times 1/2 u squared from 0 to 1 minus c dz. This will give us integral from 0 to 1 c times 1/2 times 1 minus c squared dz. Okay. And then this is equal to, let me pull the 1/2 out, integral from 0 to 1. And I will FOIL inside the integral. Okay, so I will get c minus 2c squared plus c cubed dc. When I integrate that, I will get, actually, because the limit of integration for that polynomial is from 0 to 1, you will see this is just the coefficients. You just add the coefficients of 1/2 minus 2/3 plus 1/4. Okay, if I factor it forth, the 1/12 out, I will get 6 minus times 4, that's 8 plus 3. Okay, you see, we can verify that's 1/24. So notice that I spent less time to do the inner integrals, but then slightly more time in doing the last integrations. But if you set them up correctly, then the double integral should be equal to each other. Okay, now I have to say that don't forget that the requirement of Fubini theorem, what I did here is basically applying Fubini theorem to change the order of integrations, right? Okay, but the requirement for Fubini theorems is that the integrand has to be continuous in the domain of integration and finite. I mean, I prefer to say that it's continuous, you know, but I think finite except at the integrand should be finite except at some limited, very small area. Okay, to be more precise, except at the area of size 0. But let's not talk about that. Let's just say that you look back, what's the requirement for Fubini theorem should can apply. Okay, most of the case, like the one we have here, well, the integrand c is definitely continuous everywhere, because it's polynomial at least, right? Okay, and therefore, Fubini theorem applies. You can change the order of integrations. Now, the difficult part is you need to know how to reverse or change the order of integration. Okay, let me see if we have more examples from our textbook that I can go over. Oh, yes, we do. Before I start working on a couple problems from our exercise set. Okay, I will work on example 3. This is example 3. In fact, let me also quote the picture of that situation. The situation of that situation. So we have a paraboloid. Right? E is the region, three-dimensional region bounded by the paraboloid and the plane y equals to 4. Okay, so the paraboloid, you know the paraboloid part, right? But I want to point out that the plane y equals to 4x actually refers to this part here. Okay, it's bounded quote unquote below by the paraboloid, but above by that plane. Okay, now if we project that to XY plane, if we project that to XY plane, that's what it looks like. Okay, if we project that to XY plane, that's what it looks like. Now, so if we try to set up the triple integrals, the outer two integral will be, let's see, what's the intersection here? The x will be from -2 to 2, huh? -2 to 2, and the y will be from x squared to 4, right? Okay, now then, if I choose any point in this D1 here, okay, if I choose any point in this D1, imagine this situation. If I choose any point on that D1, okay, then the solid, we will enter the solid from C is in the lower part of this paraboloid, and we will come out at the upper part of this paraboloid. Okay. In other words, if we solve for z, this z will be plus minus square root of x squared minus y, right? It will come into the solid from negative square root of x squared minus y and come out from the top part square root of x squared minus y. And the domain, the integrand will be square root of x squared plus c squared dc dy dx. But honestly, I think it's quite painful to do that though. Okay, it's quite painful to do. You can try, but in your first integral, you always have issue with this. You already have issue with it, how to integrate that with respect to z, and then you need to do c equals to x secant theta, right? The substitution, dc equals to x, oh, I'm sorry, not secant, tangent theta, and this becomes x secant squared theta d theta. No, let's stop there. That's painful. Now, instead of doing it that way, consider another order of integration. Try to find a nice one. In this case, this is too hard to execute. Too hard to execute. It feels like, you will see that it feels like how to wear our underwear or undershirt after you wear the shirt. Is it possible? That's possible, but it's way too hard, right? Okay, you need to think hard, and then you need to move in a certain way, in a very delicate way for that to happen. Instead of doing it that way, let's think in another order. Instead of projecting that on XY plane, which seems to be what this question suggests, let's project that to the left wall. Okay, and if you project it to the left wall, it's basically the shadow of this here on XY plane, right? Okay, and the shadow of that this is basically x squared plus c squared equals to 4, right? Okay, so instead, project the solid E onto XY plane. And you will see the shadow is actually a disk with radius 2. Okay, now why is it important? Well, because then all of a sudden, my outer integral can be expressed as 0 to 2 theta, 2 pi, 0 to 2 for the radius. Okay, now then in the inner integral, when I choose a point on that disk, right, and I move in the y direction, I will enter the solid E at that paraboloid, right? And then get out from that paraboloid at the plane y equals to 4. Okay, in other words, I will enter at x squared plus c squared and get out from y equals to 4. Okay, so we get x squared plus c squared dy r dr d theta. Okay, but then we will integrate this in polar. Okay, so I will change that x squared plus c squared into polar 2. That basically is r squared, right? And this is actually just r, right? That's r squared underscore, it becomes r. Okay, this is independent of x and c, and therefore independent of r and theta. R dr d theta. We integrate with respect to y first. That's basically the length of the interval, because the integrand is independent of y, right? Okay, so this is r times 4 minus r squared, r dr d theta. And notice, don't forget, that the integrand and the r is independent of theta. So yes, that will be just 2 pi times integral from 0 to 2, r squared times 4 minus r squared d theta r. To compute from there, I think it should be very easy for every one of us, supposed to be, for r squared minus r to the 4th dr. That's 2 pi times 4/3 r cubed minus 1/5 r to the 5th from 0 to 2. 2 pi 8, that's 32 over 3 minus 32 over 5. That's 64 pi times 1/3 minus 1/5. That's 2 over 15 now. So 128 pi over 15. Is that? Okay. So again, if you use the method they show us, I think it's way too hard to do though. It's way too hard to do. So instead of doing it that way, I change that into polar. Okay. We still have example 4, but I think, oh, you know what? That's a good one. Example 4. This is actually the type of question I want to go over. Let's see example 4. Express the iterated integral. So we need to interpret the solid from the triple integral. Okay, now the dx is from 0 to 1. X is from 0 to 1. Then the middle integral, y is from 0 to x squared. And then the innermost integral c is from 0 to y. Can you imagine what it looks like? Let's do the outer integral first. Okay, so the outer integral, x is from 0 to 1, and the y is from 0 to x squared, right? The parabola, part of that parabola. Now, that's the D1, maybe we call that. In 3 dimension, it looks like, in 3 dimension, it looks like this. So 0 to 1, let's say here, and then we have a part of that parabola, looks like this, right? Okay, this is y equals to x squared. Now then, as for the C will start from 0 to y. 0 to y. So 0 to y. It looks like this, I think. I don't know this. And this part here is curved. Maybe it's better if we see it from slightly different point of view. Let's say this is our x, this is our y, and this is our z. 0 to 1. That's the curve, right? And then it goes like this. Oh no, this is way too not a good point of view. Maybe from the other side then. So this is x and this is y. So this, it goes this way. This is the base, right? But then it goes this way. I wonder if you can imagine that. Like this is the vertical lines, like that. Okay, so that's what it looks like now. So difficult, huh? Yeah, that's the hard part. Okay, so we know that's the first order order of integration, dc dy dx. Can we switch that to be, let's say, the integral, triple integral of dc dx dy? So we still look at this domain, right? Okay, but instead of working with dc dy dx, we will work with dc dx dy. Now our y will be moving from 0 to 1. Okay, our y will be moving from 0 to 1. But for every y that I choose, I will get into the solid starting from that parabola and then getting out at x equals to 1. Okay, so that parabola will be square root of y, the positive branch of square root of y, and going out at x equals to 1. And then for every xy coordinate I choose, when I start from the bottom, c equals to 0, I goes up and gets out at the plane, right? Okay, so it will be from 0 to the plane z equals to y. Okay, now notice that the starting point of this guy is having the projection of the solid E, the projection of solid E on xy plane. Let me redraw it here. Okay. What if we do it with a triple integral of f x y z, that's the density, of dy dz dx. So we need to see the projection of this solid onto XZ plane first. So if we take a look here, the projection of this solid on XZ plane will be something looks like this, right? Okay, something looks like that. So y equals to 0. Oh yeah, of course. Then if this is my x here, that's 0 to 1, and intersection of this curve here. Let me kind of emphasize that. This curve here has what equation? That's the intersection of y equals to x squared and y equals to x squared, the parabola cylinder, and the plane y equals to z. Now, of course, the intersection is z equals to x squared, right? Z equals to x squared. So this is z equals to x squared. Now, if that's how we do it, x will be from 0 to 1, and then the z will be from 0 to x squared. Now, however, going back to that solid, for every xz that I choose, when I move in the positive y direction, I will enter the solid at the plane, okay, and gets out from the parabola, cylindrical parabola. Okay, in other words, I get in the plane y equals to c, y equals to z. Okay, and I get out from that cylinder y equals to x squared. Is it right? I just feel strange that we have x squared here and x squared here. Let's think about it. I think so. That's correct. Yeah, that's correct. I know that's correct. I just want you to think about it. Is it okay to have this situation? Okay. Now, instead of wondering, it's like, is it okay or not? Let's look back on how we set it up. In other words, we will never know what the triple integral will look like until you are sure that your setup is correct. Okay. If we review a little bit, our x will be from 0 to 1. For every x I choose, I will enter the get to the region here with z from 0 to x squared, z from 0 to x squared. Okay, now then for every xz coordinate that I choose, I will enter the solid at the plane, right, y equals to c, and gets out at y equals to x squared. Right? Okay. Not easy, huh? You need to be able to play this video. You repeat that maybe. You need to rewind that a bit. Okay. The good thing about recording this is that you can always pause and go back and see me explaining that in the slower motion. Okay. Now let's see if we have in different order, but not too much different. dy, dx, dz. So you will see the same position here, the same region, dx, dz, right? Now our z will be moving from 0 to 1. Our x, however, will be from square root of c up to 1. And then once we get that region covered in the outer two integrals, the inner integral will be the same with the previous one, c to x squared. Okay. Now, let's go on. There are two more integral order of integrations we need to cover. The next one I will cover is the one with dx, dc, dy, and dx, dy, dc. Okay, but for us to be able to do that, we need to first see what is the shadow of this solid when we project that on when we project that on YC plane. Okay, when we project that to YC plane, it will be a triangle, right? It looks like this. Okay, that's what it looks like, the shadow. Okay. So on YC plane, it looks like this. The y is from 0 to 1, and then it goes up to y equals to c. Okay, so the y will be from 0 to 1, and then the z will be from 0 to y. Now the hard part is, if I pick a point on this YC plane, and I move in the solid direction. Let's use this one instead. If I go to the solid, I will enter the solid at that cylindrical parabola. Okay, and then I get out at that plane x equals to 1. Okay, does it make sense for you? Okay, so I will go into the solid using that parabola. The parabola will be what? Y equals to x squared. So x equals to the positive square root of y. We took the positive branch and going out at x equals to 1. Now, then if we reverse, notice between this question and this question, right? It will be the same here. Okay, it will be 1 square root of y and 1 here. Okay, now, the c will be from 0 to 1. The y will be from c to 1. Okay, so that's the 6 different orders of integration. So I only made 5, but they give us the first one. Using that one order of integration, can you reorder the integrations into the other 5? Okay, now because they purposely use fxyz here so that we don't focus on which integral is easier, which order of integration is easier, but just do them first. Okay, now once we later on know the integrand, then you decide which order will be easier to use to tackle that problem. Okay. Let me see if we have other examples, but if no more, I will just end this lecture here. Okay, let me do one more questions from here. Example 5. Oh, you know what? Let me just go on to example 6 right away. Let me just go on to example 6 right away. So we have this. Find the center of mass of a solid with constant density. The constant density means the rho of XYZ is just constant. Let's call that rho. Okay, with bounded by paraboloid cylinder, x equals to y squared. Oh, x equals to y squared is strange. It looks like this. This is x equals to y squared, and the planes x equals to z. X equals to c, c equals to 0, and x equals to 1. Let's try to imagine what it looks like. C equals to 0 is easy. That's the xy plane. X equals to 1. Oh, if this is x here, then it is bounded by x equals to 1. Okay, so that's what it looks like on xy plane. But then by the planes x equals to c. So in 3 dimension, I try to imagine what the 3 dimension looks like. So the 3 dimension, I think, looks like this. So this is what we have on the ground. Okay, and then in the C, it goes in the, it follows the plane. So it looks like this maybe. I don't really like what it looks like there. Maybe we see it from another way. You know what? Let me just screenshot for what our textbook has. Our textbook show us something looks like this. Okay, but at least we get the domain, right? So I mean the bottom, the base of that solid. So solution. What is the mass? The mass is equal to the triple integral of the density. The good thing is the density is constant rho of, let's do dc dy dx. Okay, our x will be from 0 to 1. Our x will be from 0 to 1. Our y will be from negative square root of x to square root of x. And the z will be from 0 to x. Right? Okay. How to integrate this? The rho is constant, so I can just pull it out. Okay, integral respect to z of 0 to x, that's just the length of the interval. Okay, and then, hey, this is still independent of y, huh? Nice. Not too bad. So this is just the length of the interval, 2x square root of x dx. Aha, I thought that would be hard, but it's not. 2x to the power of 3 half dx. So when I integrate that, that will give me rho times 2 times 2/5 x to the power of 5 half from 0 to 1. That's basically just the coefficient. So that's 4 over 5 rho. That's the mass. Okay, now how about then the moment with respect to, because we want to find the center of mass, right? So how about the moment with respect to YC plane? That will be the same setup. Okay, but I insert x, right? The distance from the YC plane. I insert the x, rho dy dx. But this is equals to integral from 0 to 1. Notice that x is the last thing I integrate, right? So I can pull that x and rho out, negative square root of x, square root of x, 0 to x of rho. I'm sorry, I'm missing dz, dc, dy, dx. dc, dy, dx. Okay, so rho, no, I don't need rho anymore. I pull it out already. So this is dc, dy, dx. Now fast forward, notice that we already computed this part here. Do you realize that? Right? We already computed that part. That's integral from 0 to 1 x times rho times 2x square root of x dx, right? That's rho integral 0 to 1 of 2x to the 5/2 dx. That's rho times 2 times 2 over 7, x to the 7/2 from 0 to 1. That's, what's that? 4 over 7 rho? 4 over 7 rho. So at this point, then my x bar, the x component of center of mass will be 4 over 7 rho over 4 over 5 rho. That is 5 over 7. Okay, now how about the moment with respect to xz plane? I insert the y, right? I don't know how you learn that in your calculus too, but instead of, you start from the mass, right? Multiplied by the integrand, you multiply by the distance of the coordinate from xz plane, which is y. Okay, so I have y rho dc dy dx. Okay, that's integral from 0 to 1, integral from negative square root of x to x square root of x, rho y x dy dx. Okay, so this is integral from 0 to 1, rho x squared. I'm sorry, rho x, my bad, rho x. And then when I integrate with respect to y, I get 1/2 y squared from negative square root of x to square root of x dx. Okay. I suspect this to be 0 though. This is x minus x, right? That is 0. Which, if you think about it, take a look on the solid. Take a look on the solid. The y component of the center of mass must be, by symmetry, must be on here, right? The y component of center of mass must be y equals to 0, right? Okay. Why is it y equals to 0? Because of the symmetry of the solid and the integrand of the solid, of that, the integrand of the triple integral. Okay. In other words, when I compute the y bar, that will be just 0 over the mass, whatever it is, that will be 0. Okay. Now let's do one more. The moment with respect to YC plane. No, not YC plane. XY plane. The moment with respect to XY plane, I basically insert 0 to 1. My battery almost gone. Negative square root of x to x, square root of x, and then integral from 0 to x. I insert z instead. Okay, and you can just compute it from there. Because my battery is almost gone, I will just stop here and give you the suggested homework. That's where the devil is in the details, though. Okay, number 3 to number 18. Suggested homework 15.7, number 3 to 18, and then 27, 28, 29, 32, 27 to 34. No. 27 to, sorry. 27 to 27 to 42. I think that should be 27 to 42. Okay, I will stop here and you will see you need to do a lot of exercise here. And yeah, take a look on my supplemental videos. Okay, so long.